So I'll go ahead and get started. So hi, my name is Cyrus. I work at Lawrence Livermore National Lab, and I'm going to be talking about Vislt today, which is another one of these visualization analysis standalone tools that you can use to inspect your data. So the plan here is to have a couple slides to introduce the project. So I might cut it a little bit shorter than 30 minutes and then spend about 45 minutes doing hands-on. So the hands-on is really going to work in two different ways. I'm going to do kind of a whirlwind tour of Vislt just to give you an idea of where things lay and where things sit. So that'll be kind of fast given the window of time that we have. And then I'll slow down a little bit and we'll do a hands-on that is focused on a specific data set, which is aneurysm simulation. So that's what we're going to aim for. And we'll see how it goes and we'll adapt as necessary. So if you want to try to follow along, we're going to be using Vislt either 3.2.1 or 3.2.0. So those are the two latest releases. All the materials like the sample data sets and links to download Vislt and all those things are also on our visitusers.org page. And I think I posted that directly in the Slack for the channel here. So I think hopefully you can land on that pretty quickly. And importantly, if you want to know how to get in touch with us, we've channeled all of our communications through GitHub, and in particular, we're using GitHub discussions now. So so feel free to open up issues, and if all else fails, I think it's pretty easy to find me and email me, and I'm happy to help you out with that as well. Before we get started as well, I just want to thank some folks who worked with us to make these simulation data sets available. So the aneurysm data set's been a great one that we've used for several years, thanks to some folks at the Swiss Supercomputing Center. And yeah, it's been really nice to have this data set because it's a time varying data set, and we can kind of talk about a lot of the features of the tool using this, and it's been very helpful. There's also another one that we have available we won't look at today, but it's a very simple potential flow data set. So it's a very simple, physics example there of, flow over an airfoil. And that was created using MFEM, and it's available on our materials as well, but we won't be talking about it today, but I just wanted to thank those folks too. All right, so Vislt project introduction. So I'm gonna say, I said hello, here I am. I'm gonna stop sharing my video because that might make things a little bit easier, but I did want to say hi, and I'm gonna keep here on the audio, and we'll try to keep the chat up in case anything happens here. All right, so Vislt. So Vislt again is an application that we use to visualize mesh-based data. Vislt was created long before Google was a well-known verb. So we often joke that we made mistakes, or they made mistakes, because it was pre my time that Vislt was a very bad thing because it's very hard to actually Google and find Vislt. Of course, over the time that joke evolved to become more complicated, because now Vislt, Google knows all the things that I like, so it will always find Vislt for me, but it may not find it for you. So the takeaway here is that if you want to look for Vislt, you kind of have to Google LLML Vislt, and that should land you in the right spot. And again, we have our resources on GitHub, so searching there, I should probably recreate this exercise for that. But hopefully everything's all linked together and you can land on the right Vislt whenever you need to. So what is the tool? So it's a open source turnkey application that we use for analysis and visualization of mesh-based data. So when we say mesh-based data, we're talking about primarily the types of data that come out of simulation codes, describing things in space and having state variables painted over them. It's, for visualization experts, but mainly also for end users who are running simulation codes. They're going to use it to dissect their data. It runs on your desktop. It also runs on the world's largest supercomputers. And it is it's open source and released under a BSD style license. This picture on the right is a highlight from quite a while ago of at the time, a humongous data set, still a pretty big data set, but rendered with Vislt. I think this was on the BGL supercomputer around 2006. So in using the tool, I think Joe actually covered some of these use cases really well earlier today. I do want to point them out again, because I think it's good to think about how people use visualization tools in their workflow. The first way people use it is to explore their data. So not every simulation, unfortunately for the simulations, not everyone's going to appear on the cover of Nature. right? So it's very important to get in and have the scientists be able to understand and slice and dice and deal with their data. So data exploration is a big one. There's also features in Vislt to do, integrals and other types of quantitative analysis. That's important. Visual debugging is a really great one, and that's one of the ones that Joe has a great example about the whole propeller disappearing. Oftentimes, if you're writing a simulation code, say you have a mesh tangle or something of that nature, it's okay to have things crash and you're in a parallel debugger like TotalView or something like that. But sometimes visual context is really helpful. So being able to pick and ask things about incident nodes and elements and things like that is really handy. Vislt also provides tools for comparative analysis. This comes from your basic view graph norm, right? Obviously, you can render two pictures and use your brain, the neural network in your brain to compare them. But there's also features to map meshes onto other meshes and do subtractions. So that's a little bit more quantitative. And then finally, presentation graphics. So this is super important, right? A visualization tool does need to be able to produce nice visualizations to help communicate to sponsors or other people. So we do have support for that. As far as the types of plotting features that we have a whole bunch of them. I think the bread and butter of SciViz is pseudo-color rendering. So that's the one on the top right, which you already saw. So that's what a lot of people use. Also things like glyphing for vectors and tensors, streamlines and path lines, volume rendering, which remember is where you send rays through your data and then apply transparency based on how it intersects with your field data. There's a couple of other things. So we have some elective visualizations. It's more niche and it's certainly not powerful like other domain-specific tools. And we also have a parallel coordinates plot, and that is used primarily to help select things for other, I guess, in other contexts, so narrow things down, maybe do a threshold based on the results of a parallel coordinate. So there's a couple things here that aren't bread and butter SciViz, but we still support them. Oops. So history of the project. So Vislt started around the year 2000, supporting Livermore's multi-physics codes. So after we had success there, then we branched out and did funding through other agencies and made it open source and became a sort of a multi-organization project. So lots of people throughout the years have supported Vislt, and there's been a lot of effort gone into it. So keep going. All right, so data model. So we've talked about this a few times today. I think it's important to kind of still cement this into your head. So you're going to be presenting mesh-based data to Vislt. What does that mean? Well, there's all kinds of different ways to represent meshes, everything from simple points up to very complicated, say, adaptively defined meshes. So Vislt supports this whole menu, which is very much like the VTK menu, I think, with a couple twists and turns on it. As far as the fields that exist on the meshes, so you can have scalars or vectors. So vectors are like velocity vector would be something that you might want to plot with glyphs, right? All the way up to sort of more niche things such as material volume fractions. So if you have a hydrodynamics code that represents material interfaces at sub-element ranges, you need to have those volume fractions, and Vislt can do things like material interface reconstruction. Similarly, species is a complicated one. Really there, you're dealing with things that are atomic fractions of atomically mixed things, so it supports those. So how do I get Vislt? So hopefully you are already able to successfully get it based on the links that were shared earlier. There's two examples. So how do I obtain Vislt? Hopefully it's already there somewhere where you can use it. That could be a binary that you have for various platforms. We have been expanding the platforms that we build because we've been using Docker to build our releases, which makes it easy for us to handle a whole bunch of, say, flavors of Ubuntu. It's also installed on many supercomputing centers. So Cooley has a version. Cooley actually has a slightly older version of Vislt. I'll try to show you how to connect Cooley with that later. So if you're running on an HPC center, they may already have Vislt installed, and you might be able to access it that way. If you need to build it yourself, and this is what we do when we install it on HPC centers, and what we do when we actually build our releases, we have a script called build Vislt, and it will build all of the third-party libraries that we have and Vislt itself. We also have a little bit of support for building with SPAC. So you can't build all the features of Vislt with SPAC, but we'd like to build that up over time. But for now, build Vislt is sort of our hardened solution for doing our releases. How do I get my data into Vislt? This is another important one, right? So Vislt supports over 100 let's just say over 110 different file formats. That's everything from, a well-defined format, something like VTK, to, random person down the hall really needed it for important work. So there's a whole bunch of different flavors of file formats. And I think if you even think about, this is a complicated data modeling issue, right? People say, well, just use HDF5. Well, Vislt probably has at least 20 different flavors of HDF5 data that it reads. So how do I do it if I'm starting from square, from basically nothing? So if you have like columns of data like CSV, there's something called a plain text reader that you might be able to poke around with. The best thing probably to invest in is to write to a commonly used file format. So things like VTK or Silo. So if you write to VTK file formats, you'll be able to use them in Vislt. You'll also be able to use them in tools like ParaView. We've been focusing a lot on this new data format, which is based on the conduit mesh blueprint. And that's been a lot of our reader works on there. And this is also the way that the data is presented to Ascent, which was mentioned earlier. And there's also a little script that might help you out. We have a whole manual on this. If all else fails, there's a whole bunch of different examples. So Vislt has a plugin architecture that will allow you to go ahead and build your own. So it's Vislt's not just an application; it also is a platform for doing building custom workflows, we say. So so we have the C++ plugin architecture. That's how you can extend plots operators and also write custom file formats. There are ways to do custom interfaces in Python, C++, and Java. For Python, we have scripting and batch processing, which are super important. So that's how a lot of people do the fanciest movies, right? We turn our actions into Python scripts, and we can submit those and have those go and ask Vislt to do and make beautiful visualizations. We also have some more advanced ways to get at the very core of the data in something called Python expressions and queries. For in-situ coupling, Vislt has a library called libsim. So this is a in-situ capability that we've had for quite some time. We're investing now in Ascent. So Ascent is our next generation capability, but libsim still exists. Libsim allows you to connect to all of what Vislt offers. And Vislt's also been used as a platform to deploy visualization research over the years, which has been great. So we don't want research that's really good in the visualization community to never reach the hands of users. So I think some particularly impactful research that's been deployed has been the integral curve and I guess the advanced streamline capabilities that were in Vislt. And some of those were customized for particular communities, like the Fusion community, for example. Right now, we've been focusing a lot on in-situ processing and basically porting to new architectures, I guess you could say that, in using GPU systems and things of that nature. And so we're involved in the ECP and also involved in some other endeavors like this, like the SciDAC program. So this was a little while ago, but it was an important peg post for us. So for Vislt 3.0, it was a big release for us in 2019. And the focus was also updating our software development process. So as Vislt evolved throughout the years, we kind of had a piecemeal of things that were, lowest energy to use. So we had a bug tracker at Oak Ridge. We had a mailing list at Oak Ridge. We had our wiki, all these other things. So we've consolidated a lot of those things to use GitHub, since GitHub's now available, and it's a very easy platform for people to join. We also refactored all of our docs to use Sphinx, so that's been nice. And now those are all hosted on Read the Docs. So we have our main user documentation all up there. And there's still some things that need to be ported, but it was a very large effort to get this done. And finally, so our latest release includes Python 3 support. So Vislt's had Python since the beginning of time. Well, the beginning of Vislt time, right? Early 2000s. So so it was actually quite a bit of an effort. I mean, there was certain idioms in Vislt that were, even ancient Python 2 that we had to attack. So we got all this now, and now we're building with Python 3 by default. As far as parallelism, so Vislt uses MPI to scale up. The way to describe this conceptually is, on our left here, we have this full data set, which is the one that we saw earlier, that it consists of 20 billion elements, and the way it's distributed across the supercomputer you see here on the right. So it's spatially partitioned. And, what we want to see is the picture on the left. The picture on the right is great for debugging, but ultimately, if we're going to be making the visualizations, we want to see this as a coherent data set. So the algorithms in Vislt are designed to do that, right? To scale up, we use a client-server architecture. So we have a viewer which manages all the state, and then we have different clients, which are like our GUI, which you'll see a lot of in our command line interface, which is Python-based. And they talk to an engine which can run in parallel, right? So the parallel engine can either run on your desktop or it can run on an HPC cluster. It's going to do the heavy lifting. It's going to load all the data and do all of that scalably. So it will work just fine for large data. So another important feature is that Vislt can switch to scalable rendering when you have really big data. So if you have small data sets, even if you're running remotely, it can ship them back to your, say, your laptop and then use the graphics card there. But at some point, that just gets to be too onerous. So when things get too big, it switches to parallel rendering, and then it can do parallel compositing. So this image here just describes that process, right? Your data is partitioned across these different tasks, and the parallel compositing process knows how to take, the final pixels and put them all together. So, and similarly for volume rendering. So this is surface rendering is an example of this here, right? But for volume rendering, you have a bunch of arrays. You need to partition those out, and we need to do that scalably as well. So Silvio mentioned that, as a community, we're doing a lot of interesting things. And I think that what the takeaway here is that, to try to get to exascale, we're really investing because it's a heavy lift. So there's two big things that are going on here. So dealing with node level parallelism. So predominantly, everything has been MPI parallel to scale out. And now we have, for several years now, we've had GPUs, and we also have lots of different types of GPUs or heterogeneous computing. We need a way to have a common set of algorithms that can run across all those things in a performance portable way. And VTKM is an effort that's helping do that. So we're leveraging VTKM and tools like ParaView and Vislt and also Ascent. So as sort of a core capability for making sure that we'll be able to run on the fanciest new devices that exist in supercomputers around the corner. So that's one aspect of it. And then the other thing is that IO is getting scarier. So we're focusing a lot more on in situ. And there's a lot of different in situ infrastructures and algorithms that are underdeveloped. So I work for the Alpine project, was an ECP project, which helps develop infrastructure and algorithms. Actually, a lot of the effort is focused on really interesting algorithms to help you summarize data in particular ways. But in addition to that, there's a bunch of different frameworks, right, that are used to do the actually deploy in situ algorithms. And so Silvio mentioned Sensei, and I'm one of the main developers of Ascent, and we'll talk a little bit about Ascent later. There's also Catalyst and LibSim. So we're investing a lot in both a tool called Conduit and Ascent, right? So this is basically, the Vislt team at Livermore has basically created these tools over many years and collaborated with a lot of folks to bring them to life. So these are what we're really excited about. So Conduit is a tool that gives you a way to describe in-memory data and exchange it with other people. So that's a tool that we've been developing for a while. And then also Ascent, which you've heard a little bit about, is a flyweight in situ visualization tool. So to do things like ray tracing and rendering for HPC simulations linked directly into their code. So a little bit about Conduit, just so people have some context. So mentioned, it gives you an intuitive API for representing in-memory data. Really what it is it's a way to hierarchically organize arrays. That's probably the simplest way to think about it. And importantly, you can describe arrays without Conduit actually having to own them. It can own them, it can copy them in, but you can also tell them, hey, this is a pointer here. Think of it as giving it a name and information about how it's strided. Conduit provides C, C++, Python, and Fortran APIs. So the APIs and Conduit are meant to be a good subset of features that can be used across these codes. And then beyond that, we also have shared conventions for exchanging things as part of these trees, because these trees can be pretty much anything you want them to be. They can be completely dynamic. So we have ways of presenting a simulation code in one of these trees and rules related to that. And that's actually called the mesh blueprint. Also, we have IO interfaces. So once you've described these trees, it's really easy to move them around. And we use that for lots of different things. So Conduit's also used not just for visualization tools, but it's used in simulation codes that look more for like their binary checkpoint restart, and also shipping things around with MPI. So Ascent, what you've heard a little bit about, is a new in situ visualization analysis library that we're investing in. We really focused on making a smaller tool and focused on a couple different use cases. So getting the pictures that you want made, transforming our data, so things like isosurface and all the things, and then finally getting data out of Ascent, whether it be to launch it into a different ecosystem like Python, or also writing the files. So we're going to show you some examples of Ascent later in the Jupyter section. So I think that'll make a little bit more sense now, but just to provide a little bit of context, it's also C, C++, Python, and Fortran. And the big takeaway here is it's kind of built from the ground up to do distributed memory and mini-core well. So we've already been able to demonstrate this on, several years ago, actually, at this point, we were able to demonstrate doing some clipping and isosurfacing and ray tracing across over 16,000 GPUs on Livermore's Sierra system. It's a little bit simpler, so it doesn't have the long tail of features of something like Vislt, but it also has lower memory requirements and less dependencies. And for that, we're focusing on SPAC for building it. So that's kind of the project introduction. Before we dive into the GUI, I'm going to give you something to anchor you a little bit about thinking when it comes to doing things with Vislt. So in Vislt, we have 5 different abstractions that the interface is built around. And here they are, and you will hear me say them over and over and over again, because I'm trying to make associations here. So, but here they are. Let's get started. So databases are the abstraction that are used to read data. So if you if you have a file format, you're going to use a database to get it in. Plots are what we use to render data. Operators manipulate data, so that could be something like a slice. And 2 other important ones, which are very powerful. So expressions, which allow you to generate derived quantities. So say you only had density in your output mesh. Well, Vislt could calculate the per element volume, and it could also scale density by that, and you could have per element mass. And that's an example of an expression. Or you could take a gradient of something that was published. That's an example of an expression. And then finally, there's queries, which do data summarization. So now that I have the mass, sum it all up. So here's a couple examples, and you'll see me do things like this when I actually fire up Vislt. So the simplest thing we can do is, if you have a database, you can open it up and you can make a picture. So I can open up an HDF5 file and I can make a pseudo color plot of, say, density, right? But I can also transform the data, right? So in this case, I can add an operator. If it was a 3D data set, I can slice it down to maybe take a 2D slice. And now, instead of plotting the entire data set, I'm plotting the slice of density there. You can chain operators together. So say we want to elevate it after we've sliced it, right? So now we're creating pseudocolor of density that's been elevated and sort of spatially distorted. We can also define expressions. So right, in this example I talk about here, if you publish a velocity vector, well, maybe you want to do a pseudocolor plot of its magnitude. So you can derive the speed, which is the magnitude velocity, using our expression language. You can also query. So at the result of a plot could be queried. So you could say integrate density to find mass. And then you can do all kinds of fun things, put all these together in a way that makes sense for what you're trying to do, what types of questions you're trying to ask and answer. So databases, plots, operators, and expressions and queries. That's what we're going to be showing you. And in the slides, you can see my contact info. I'm going to pivot here to start doing hands-on with Vislt. But yeah, so the slides beyond this, there's a lot of different links that if you wanted to look at, you can get to. And then there's also some slides here that are similar to Joe's introduction slides, right? He does a really great job introducing this, so we don't talk about this here, but we have some of that material too if you're interested in the different types of menu of options that we provide. All right, so let me get Vislt fired up here. So I have Vislt. I'm on a Mac, so I have Vislt on my desktop. And once I've dragged it there and install it, I can just double click on it and it will open for me. The procedure is a little bit different for Linux, or a little bit different for running on Windows, but hopefully we'll be okay. So while it's starting here, I'm gonna get a drink of water real quick. All right, it's not liking me right now. Okay, so I want to make sure that people can see this. Okay, can someone just type in chat that it looks okay to them? Hopefully
We can see it.
Good. All right, great. So, okay, so here's Visit here. Here's the application. I'm going to move it down a little bit so Zoom doesn't keep popping in my way here. So when you start Visit, you're presented with two different windows. So this window here is called the viewer. That's where you're going to interact with a lot of your visualizations. And this is the GUI over here. So that's where we set up and control everything. So the first thing we're going to do to get started is we're going to click Open to open a database. This is just a file browser, and I'll show you, I think I will have time. I will try to show you how to connect to Cooley. And to connect to Cooley, you would basically select a different host and type in passwords. But for now, we're just going to do everything locally. The sample data sets are pretty small. So I have the data here already extracted for me. So the tutorial data comes in a couple different packages or zip files. So there's the aneurysm data, which we're going to use, and there's also tutorial data, which I'm going to use right now just to show you around quickly. Again, the plan is I'm going to give you an idea about Visit by showing you a bunch of different features in a little bit of a quick way, and then we can slow down a little bit and we can try to do the tutorial for the aneurysm data together, which is more prescriptive. And actually, the aneurysm data tutorial is very well outlined on our documentation. So you can always follow along with that later if you wanted to as well. So I'm going to start with the tutorial data, and I'm going to open a file called example.silo to get started. So by default, Visit will guess what the file type is. Remember, there's hundreds of different file types it could be, but it'll guess by the extension, or actually will guess by sometimes data in the file. So I'm going to open it. I hit OK, and then nothing happens. So this is where people say, well, what's going on here? So we want you to be explicit about what you're asking Visit to do. So the example.silo could have all kinds of different variables, all kinds of different meshes in it, right? And we really want you to tell it to do something before it does something. So by default, we do nothing. So the first thing we're going to do is actually create a plot. So we opened a database. Remember, databases are how we get data in, and we're going to add a plot. Plots are how we render pictures out of Visit. So if I hit add, there's all this different menu of plots here. We'll cover a couple of these today, but I'm going to focus on pseudo color first. In the pseudo color menu, I have a whole bunch of different options here. These are actually the variables that are published to Visit through the database. So I'm going to take a look at temp, and I added a plot of temp, and still nothing happened. So again, we want you to be a little bit explicit. So you have to tell Visit, please draw. So I click draw, and now we're in business. We actually have our plot here. So example.silo is just a cube with a couple different fields on it. Actually, there's some other meshes in there as well. This example is just a pseudo color plot of one of the fields, the field temperature. We can control the different properties of the pseudo color plot by expanding this arrow here and clicking on pseudo color. So the takeaway message here is that we have all these different attribute windows that you can get access, and that's how you tweak things, right? So if I wasn't happy with my color map, I could select one of the other color maps, for example, change it. And I can also do things like peg the minimum or the maximum value, of my color bar here, and make different changes based on that, kind of control the view. So pseudo color plot is a basic plot that people use all the time. Another interesting plot that people use a lot is the mesh plot. So that actually will show the mesh topology. So if I go to add another plot, in this case, I want the mesh called mesh. The other ones are different meshes. So this is the one that's associated with temperature. And I draw it. I will be able to see, in this case, the hexes that build up this mesh, right? And I can zoom around with my mouse and my keyboard. And if I get into trouble, up here on the viewer, there's some view options that can help me out. So this one up here will reset the view to some default view. And then there's also get back to my last view. So like the panic button, right? And there's a couple of different ways to do that. So I don't know how big the stack is that it keeps, but it keeps quite a few. So just like the pseudo color plot, if I go into the mesh plot, if I expand, I can change a couple different options, right? So I could change my mesh color, which is the color of the lines, to be a different color. It's probably a bad choice. So let's make it slightly different. All right, so what you're seeing here is that we can plot a whole bunch of different plots together into kind of one coherent image, which is nice. Before I forget, I want to show you how to actually render out and save an image, because that's important. Sometimes I do forget, and then I feel bad. So to render out an image, we go to File, and we go to Set Save Options. So this is where we can select our, what type of file format we want to have, and also select the resolution of that we want to render at, which can be independent of what you're seeing on the screen. So I can save out a file. I'm going to save out a file called mycube. If you keep this family checked, what that will do is every time you save out a file, it'll append a new number to it, so you don't accidentally overwrite things. So I'm going to save my cube out. I'm going to save it out at, say, 2048 cubed. Hit apply here and hit save. Visit actually told me down here in the status bar that it saved mycube.png. And let me try to take a look at it real quick. Get a new terminal here. And here it is. Here's the picture that I rendered out. Similarly, if you wanted to make a movie, there is actually a movie wizard in Visit that you can use to do that. I'm not going to show that right now, but just that's also under File, Save Movie. So once you've set up your save options, you can also just hit Control S if you want to keep rendering things out, and it will keep rendering out pictures for you. So a couple other things in terms of making things a little bit neat and tidy. So under the controls menu here, we also have options to change the annotations. So if you really don't like the fact that it's showing your username here on the bottom right, you can take that off and hit apply and it will go away. Similarly, you can turn off the axes, things of that nature, right? So, there's not a whole bunch of different controls, right, for making annotations super fancy, but there's enough to customize things. I think for the highest end movies, we usually use Visit to render, and then we will actually put annotations in after the fact, using Python or some other tools. Also under controls, there's other things you can do like lighting, right? So if you want to change how the lights are interacting with your data set, you can control those here, or you can add multiple lights. And you can really wash things out if you get too crazy here. So takeaway here is that options menu our controls menu has access to all of these different things that help you have more fun with Visit and get more accomplished. So let me go back and make sure I haven't totally, I'm gonna take this light off so in the future we don't have to deal with that. Okay, so there's different pick modes, which I mentioned are part of the sort of the debugging capability. So I can do a zone pick if I click on my mesh here. If I click on this little cross here with the Z and I click on my mesh, it will pop up a window with more information than I possibly could need right now. It also annotates the mesh with a little pick point here to tell me what this data is. And if you want to, it's also possible to pick other variables when you do this. So I was plotting temperature, but if I wanted to actually plot pressure, I can put it in here, and then I can go back and click again, and I will get pressure and I will get temperature, right? So this is important. You can also get the physical coordinates if I pick on something, so it will tell me, oh, all the nodes, here's where they are in space. Super handy if you're trying to actually, really dive deep on small details. There's a couple other modes that exist. So mainly there's a navigation mode here. This is where your default, where you can drag things around like with a trackball type of interface and zoom with your mouse, right? There's also a rubber band zoom, which will help you, zoom in. It's useful more in 2D, I would say, in 3D, but still handy in 3D. And then there's also a line out, which I'm going to show you in just a minute. So we talked about databases, we talked about plots. Now let's move on and we're going to talk about operators. So we're going to change our data in some way. I'm going to get all these pick points off. So the viewer here has a context menu as well, and we can use that to reset if we panic, or we can get to clearing out things like if we have those pick points on there. So operators. So much like plots, we have a menu of operators. So these are going to be put into our pipeline here and executed. I'm going to show you a couple of them. So the first one I'm going to show you is under the slicing category. It's the slice. And, you know, to no one's surprise, what it does is it takes a 2D slice out of a 3D data set. When we add an operator, we're back to this green state, which means we need to tell Vislt that, yes, we're done and we'd like you to actually draw things. So if I click draw here, I will now see a slice. This might look similar to you, but it turns out we're actually in a 2D view here. And here's where I could use my zoom to go in a little bit more intuitively. And now we can actually do this line out here. So if I click on this mode, I can click and drag a line out across my 2D plot. There's ways to do 3D line outs as well. Usually you might want to actually type those in into our query interface. I'll try to remember to show that. But so here is a line out. If I drag it, I get a new window, which gives me this data set of my temperature and its peaks in different places over time. So I'm going to close this and go back. Just like the pseudo color plot had and mesh plot had its attributes, well, the slice also has its attributes, right? One important one is this project to 2D. If I turn that off, you can actually see where the mesh is in 3D, right? So I was slicing on the X or Y axis before, but I could change that to the Y or Z or whatever. And in doing this, you can see where it is in the context of the original 3D data set. Sometimes it doesn't matter. Sometimes you want it to be 2D because you want to interact with that slice in that way. Other important operators, and we'll cover this a little bit more in the aneurysm tutorial, but things like doing contours. So there's a couple different ways to do contours. You can do a contour plot, which will assign unique colors to each contour, but I like to use an isosurface, which allows me to do a pseudo color plot and then select the surfaces, the contours that I want to pull out, and still color it by the values that are on the field. So if I go to operators, slicing isosurface, I add that. There's a bunch of different options here. I'm just going to leave it at the default, which will give me 10 equally spaced levels. And draw it. Now we can see our data set and we can see the contours that were defined by the fields painted across the mesh. Let's take a look at another plot real quick. So volume plot is how you do volume rendering. So I'm going to do a volume plot of temperature. So I'll just draw here. So doing volume rendering usually the art there is in defining the transfer function. So I went to my volume attributes. I'm going to go to the transfer function. I'm also going to change my color table here to something different. Transfer function shown here shows you kind of a histogram of the data, and you can kind of just scribble and figure out what you want to highlight. This tells you how much opacity you want to apply if you hit that value. So in doing this, we can dial things down and we can make some pretty interesting looking visualizations that are actually sending rays effectively through our data. Okay, so still a couple more things I want to show. Quickly, I want to show the filled boundary plot. So this plot involves material volume fractions, which this data set happens to have. So this has a set of materials here. There's actually two materials. If I just plot the plot directly, it's a little bit boring. It says it's all air. So what's happening here is there's actually another set of volume fractions that are embedded inside of the mesh, and it's doing an interface reconstruction, but we can't see any of them, so it's not going to show us those. If I click here next to the arrow, there's these circles that are overlapping. They actually are supposed to be a Venn diagram. So if I click on that, I can actually get to a subsetting menu, and I could do material selection myself. So here I find that there's two materials here, and I could turn off air since it's blocking us, and we could take a look at chrome. So chrome has this funky pattern here with that's embedded via volume fractions, and when I do that, it will do the material interface reconstruction for me and show those interfaces as an unstructured mesh. Another way to take a look at this is I could slice it. So we'll look at another slice, which is a 3 slice, so it's 3 orthogonal slices. And now I can see inside a little bit differently. You get my light back. No, let's get my light back in front here. Easier to see things. And if we zoom in, we can see, so this mesh was originally a regular grid, but it's actually reconstructed the interfaces here. So we have something that doesn't have, a regular grid anymore. It actually has more complicated geometry. Plots, operators, and databases, we've talked about. 2 more things to talk about: expressions and queries. So let's do expressions first. So if I go to controls expressions, I get an editor here. And what this is kind of a little bit of a domain specific language that allows me to define mathematical expressions to derive, some new fields from existing fields in my data set. So in this case, I'm going to create something called Tgrad, which is going to be the temperature gradient. The output's going to be a mesh because it's a gradient, the output's going to be a vector because it's a gradient, excuse me. And I'm going to use a built-in function here, gradient, and I am going to do that gradient on my temperature variable. This gradient is a built-in function. There's a lot of them. There's kind of the menu here shows you all of them that exist. But we could also, if we wanted to, we could also take like the magnitude of this and make a scalar output. I'm not going to do that just yet, but you can combine things together, right? Or if you had two vector fields, you could subtract them, things of that nature. So I'm going to apply this. And now I have a new variable I can plot. It's a vector variable, so I can only plot it with the vector plot for now, but it's called Tgrad. So if I create this plot, which vector plot is going to be showing me, glyphs, so little arrows. If I draw them, I can now plot the vector field. Let me get back to my window here. I'm going to actually play with this a little bit just to make sure you can see them a little bit better. So by default, Vislt doesn't like to draw lots of glyphs because it can overwhelm things, especially if you had a 1 billion element data set, you're just going to end up with a mess. So, but what we're seeing here is we're seeing the gradient of that temperature variable, and we're seeing the different vectors plotted from that. And that gradient was actually calculated by Vislt on the fly. It was not available in the data set, or restated. Maybe it was in the data set, but we still use Vislt's features to recalculate it. So another example of doing, like I mentioned before, is you could calculate the volume of each element and scale that by density and plot a per element mass. All right, let's see here. Actually, I will show you real quick. Let's see. I'm going to make a magnitude of this, so Tgrad mag. So I can do magnitude of my existing expression that I created. So I created Tgrad. I'm going to take the magnitude of Tgrad and make that a scalar. And now I can plot that as a pseudocolor because it's now appears as a scalar variable. So Tgrad mag, here it is. All right, so we can see the areas where the gradient was high. So expressions, pretty powerful. You gotta, think about, you have fields on your mesh, you'd like to combine them somehow to paint new fields on your mesh. That's the way to think about it. All right, last thing are queries. So real quick, I'm just going to put up a pressure plot here. And queries allow us to do data summarization, ask questions, and get sort of a summary answer. So if I go to controls query, there's a whole menu of them here, from simple things to complicated things. Let's ask some simple things first. So let's ask the min and the max. So I can query that and it will give me some information here. It says the min pressure exists at this place with this, or at this node with this coordinate, and here's the max. There's a difference here between original and actual data. So this is important if you want to toggle between, say, you've taken a slice. So let me just demonstrate it. So let me add a slice here. If I query the actual data now, my result will actually only be on the slice. But if I flip back to the original, I can compare that against the result from the entire data set. This can be handy if you're trying to understand the differences between different regions in your data. But the takeaway is that if you've changed it with an operator or anything at all, you probably want actual data. So you want to constrain things just to that slice. And we can see that that on the slice, the range is different, right? Because we didn't happen to have that min value on this slice. And we didn't happen to have the global max on this slice either, right? So it's winnowed in a little bit. There's other interesting things you can do. So for example, if you cut your mesh, let's cut our mesh with isovolume. I'll tell you a little bit about this later, but let's get a picture up here. Uh-oh, I did it wrong, sorry. There we go. So if we cut our mesh into a whole bunch of different pieces, we can ask questions about the number of connected components that exist. So it tells us, hey, there's actually 23 connected sub meshes. You can get statistics about all of these. So so there's a whole bunch of different connected components queries. So if I ask this question, I will actually get an output file, or through Python, I could get, say, the bounding boxes of each of these particular things. So all the queries are categorized into different menus. So if you're asking questions about a mesh, you can go here and say, okay, what's my surface area, or what's my total number of zones, total number of nodes. If you're asking questions about variables, you can ask questions about min and max, like we already showed. There's also ways to sum up all the variables. So that's a way, if you had, say, your per element mass expression, you could sum it up and get the total mass of the data. So queries, you can ask these questions and you typically get an answer out that isn't on a mesh, right? It's reduced greatly. All right. Now we're about to go into the aneurysm stuff, but I have to show you something very important before that. Python. Python is super important for controlling Vislt. And the way we typically do that, so Vislt has a command line interface that you could run. You basically, when you run Vislt, you can say Vislt -CLI, and that'll pull that up, and it has an embedded Python interpreter, and you can type things and learn things about the Vislt interface that way. The best way to learn, though, is typically by recording your actions in the GUI and turning those into Python scripts. So I'm going to show you how to do that first, and then I'm going to show you a couple example Python scripts that we already have, to tell you some of the basics. But first, let's record something and turn it into Python. So what I want to do is I'm going to go to Controls, and I'm going to go to Command, which pops up another window. And these windows are different scratch pads here for Python scripts that we can run. I'm going to go to an empty one, and I'm going to say record. When I do this, a new command line interface will pop up if one's not already connected. So that's it. There's Python there. Now everything I do in the GUI here, until I hit stop, will be reflected in Python right here. So if I hit add, I'm going to do my pseudo color of temperature. And let's say that we wanted to change the minimum, kind of like we messed with before. And I hit apply, draw, and let's move the view. All right, when I hit stop, I get a flow out of all the Python that sets everything. Now this is pretty verbose, right? Because it's basically setting absolutely everything about the pseudo color plot. So sometimes the recorded things can be pretty verbose. Usually they can just be culled down. You'll notice it also captured my camera here, which is great because I did move the camera. So we want to be able to capture those things. But starting from here, you can craft things, and you can craft them into reproducible scripts, right? And you can also run those in batch without any windows or anything like that, with lots of processors, and render things out overnight, for example. So it's super powerful. So let's skip back to a simple example, not using recording, but just of looking at the Python API as it is. So I'm going to start here. So this example is also in our, you can link off to this, and you can link off to GitHub and see this. Hopefully it's big enough, but I'm just going to describe what it's doing real quick, and then we're going to actually run it. So in this case, we're calling delete all plots just because we're going to run this script a couple times. We want to start from ground zero. We're adding a plot pseudo color of our temperature variable. We draw that, and then we get the pseudo color attributes. So you can think of this as being the analog of me clicking on that pseudo color menu, right? Or pseudo color attributes window, and having that pop up and playing with settings in there. So I'm going to run this. So we're going to create temperature and we're going to change basically the legend and the way the pseudocolors apply. So I hit execute and we see we have our plot here. And if I were to go in here and look at our pseudocolor attributes, we can see that those values are what were reflected in my Python script here. So that's great. Let's go a little bit further. Second example. This example, we're going to play around with changing the attributes of an operator, in this case, the isosurface operator. So you saw me draw an isosurface before where we had a whole bunch of different isosurfaces. What this does is it actually animates the isosurface contour value so that you'll see it sweep through a range. And when we do this, you get kind of an animation through all the iso contours. Now, if you wanted to, you could just throw a save window here and you'd get a PNG for each one of these. And that's the way you can start to begin making really interesting movies, right? So we'll just play this one more time. So by combining Python and this interface, there's a whole lot you can do. There's a couple more examples that show like how to set the camera and fly around and things of that nature. So if you're in the documentation, you can follow those. Want to just show one more, which is my favorite example because it also shows all 5 of the building blocks here. So we're going to get rid of all the other plots. That's great. We're going to add our pseudocolor plot of temperature, apply a 3 slice. So what we're going to do here is get a 3 slice and shift those planes back so it kind of looks like we have a diorama or like a little box that's going to be around the more interesting thing, which I will tell you about in a second. We're going to run a query to get the max value because we want to demonstrate a query. We're going to define a vector expression of the gradient. So in this case, it's just like what we did before, but we're calling it G. And we're actually going to do streamlines of that gradient. So that's what this is all about. So we're adding a plot of this integral curve, which I'll tell you about in a little bit, setting up some different seed points and making it look pretty. So let me execute this again. And so running this script, here's the result. So we have this kind of interesting looking field where our streamlines are kind of going to sinks in this gradient field. Again, we have 2 plots here. So if I were to hide the streamlines, you would just see that diorama that I talked about. And then that's the 3 slice. So, so in a nutshell, that gives you an idea of some of the stuff you can do with Vislt and Python. And again, you can run this in a completely different way than I'm doing it here. I'm just showing it to you from the GUI because that's really an easy way for me to present it to you. But you can also run things with -CLI and you can say -S and give it your favorite Python script, and it'll go on doing fun things. All right, so here we will now transition to talk about the aneurysm data set. So let me close this. All right, so I'm going to open it up to get started. So this data set has 200 different time steps. They're all silo files and they're grouped together with this file called aneurysm.visit, which basically just lists them. But nice thing is we have a time varying data set here. Again, I'm going to go through a couple of steps here. I'll try to go a little bit slower, but everything is very laid out in a prescriptive way on the docs. So if I missed a step and you need to go back, you should be able to get there. So I'm going to open it up and we're again at a point where nothing's happening. One of the different things we see here than before is we have this time slider. So the time slider will allow us to select any of our 200 steps. If you had a data set with 1,000, you'd be sliding along 1,000 steps. And let's first take a look by trying to understand this data set. So this data set, we know it has something to do with blood flow. Let's take a look at a mesh first. So we have our mesh. I'm going to draw that. Take a look at it. And from what we see on the outside, we see what appears to be a bunch of different triangles. However, this is a volumetric data set. So turns out we're actually looking at a whole bunch of tetrahedra here. So this is our mesh. Let me reset the view here. So we'll find out later that the blood flow is pumping through here and kind of swirling around. And this is the section where there's a problem, where there's a aneurysm in the vessel. So with the mesh plot, I can play around with different options. You saw me do this earlier. So I could change the colors of the mesh lines if I'd like to. There's nothing stopping me from picking bad values. So remember that. I can also change the opaque color of the mesh. So if I wanted to basically the opaque color is the part that's not see-through. I can also turn opaque off, right? So you could see directly through, and then you could see the other side of the outside of the mesh. Is one way to think about it. If you're really brave, you can turn on show internal zones. And yeah, it's a pretty dense mesh. So now we're seeing every single one of those tets drawn, but it's kind of a mess. So not really useful in this example. So we have our mesh. In this case, let me get back to something that's a little bit more more useful here. We have our mesh. In this case, if we look over time, the mesh isn't changing at all. So this is a kind of a static mesh over time where the fields themselves are going to be evolving on that mesh. So think of it as an Eulerian mesh. And so great. So the mesh isn't super exciting, but we can still ask a couple questions about it. So I can say, hey, I want to know something about how many nodes there are, how many zones there are, right? I can do that with our query interface. So I can ask, let me go to all. I can ask, so the number of nodes, let's see.
Hey, Cyrus?
Yes, yes.
Hey, I'm sorry to interrupt you. Would this be a good time to maybe take a break? So we have our next speaker, Scott, has a hard stop where since our schedule is slipped some.
Okay.
Is that can be too disruptive if we switch over to?
No, I think it would be fun. I'd be happy to do that. We can go ahead and we'll look at the fields of the aneurysm. If we could do that a little bit later, that would be great. Could we gonna have a little bit more time? Is that okay? Or just
yeah, we can pick up where you left off and give you some additional the rest of the time that we had allotted for, but because
sure.
because we slipped by about 25 minutes, getting started, we have a
yeah, sure. Happy to do that. That's fine. So I'll go ahead and we'll stop here. And I'll just remember what we'll do is we'll pick up looking at some of the variables on the aneurysm data set. And this will also give me a chance to maybe ask some questions that maybe have been queued up.